Hello and welcome to Lecture 5 of our Essentials of Semiconductor Device Physics course. In this lecture, we're going to answer the question, why does energy flow from a hotter to a colder system? So last time, we considered two systems, A and B, in thermal contact and isolated from the universe. And we learned that the states of the total system are formed by combinations of states of system A with states of system B so as to keep the total energy constant. And we also learned that the most probable energy, the energy of equilibrium, is the energy satisfying this condition, that the temperature of system A is equal to the temperature of system B. So this is the condition characterizing thermal equilibrium. This time we're going to consider the same situations before, a system A in thermal contact with a system B and the total system isolated from the universe. But now we're going to take a look at what we can say when the two systems are not in equilibrium, when they are out of equilibrium. Okay, so let's suppose that the demon who made the list of states of the total system collected all states in which system A has the most probable energy within this box. So recall that according to the fundamental assumption of statistical physics, all states are equally probable within or without the box, but that there are so many more states of the total system within the box than states outside the box when the total system is macroscopic, that we can be certain that we're going to find the total system in a state within the box. In other words, in a state in which system A has the most probable energy. In other words, in which system A has an energy satisfying this condition. Now let's suppose that we have just prepared systems A and B and they have not reached equilibrium yet. So let's suppose that at time t equals 0, their temperatures are different. So in this case, we cannot use the fundamental assumption of statistical physics. For example, let's suppose that at time t equals 0, this is the state of the total system. And then we ask, what will be the state of the total system after some time, which is sufficiently short so that only one coin can exchange energy with another coin. So if we waited a time that is so short that only one coin exchanged energy with another coin, then we cannot say that the new state will be any state of the list with equal probability, because in this case, the new state will be a state that is very similar to the original state, since we let only one coin to exchange energy with another coin. Now, if we wait a time sufficiently long so that all coins can exchange energy at least once, then we can say that all states are equally probable. In other words, if we wait a time which is sufficiently long for the systems to reach equilibrium, then we can say that all states are equally probable. So the fundamental assumption of statistical physics only applies when we have waited a time sufficiently long for the systems to reach equilibrium. But even though we cannot use the fundamental assumption to study systems out of equilibrium, we can still predict how they will exchange energies as they evolve towards the condition of equilibrium. And this is what we're going to do in this lecture. We're going to ask the question, is it more probable that system A will send energy to system B, or is it more probable that system B will send energy to system A? Okay, so we want to know what is the most probable direction of the energy flux. And to answer this question, we're going to assume that system A and B exchange delta U units of energy. So in this notation here, UAN is the new, N for new, energy of system A after it exchanged delta U units of energy with system B. UA naught is the initial energy before the exchange of energy, and we have the same for system B. So notice that the sign of delta U defines the direction of energy flux. So if delta U is positive, that means that the new energy is lower than the initial energy. In other words, energy is flowing from A to B. And if delta U is negative, then the new energy is higher than the initial energy, which means that energy is flowing from B to A. And we also have two possibilities. The first possibility is that there are more states of the total system in which the new energy is lower than the initial energy than the other way around. And the second possibility is that there are more states of the total system in which the new energy is higher than the initial energy than the other way around. Now, if the first possibility turns out to be true, then, in other words, if there are more states of the total system in which the new energy is lower than the initial energy, then it is more likely that the new energy will be lower than the initial energy. In other words, it is more likely that the sign of delta U is positive. In other words, it is more likely that energy will flow from A to B. On the other hand, if it turns out that the second possibility is true, in other words, if there are more states of the total system in which the new energy is higher than the initial energy, then it is more likely that the new energy will be higher than the initial energy. In other words, it is more likely that delta U is negative. In other words, it is more likely that energy will flow from system B to system A. Okay, so we have concluded that to find the most probable direction of the energy flux, in other words, to find the most probable sign of delta U, we need to identify which one of these two possibilities turns out to be true. Now, to identify which one of these two possibilities is true, we need to inspect the multiplicity, because the multiplicity is the number of states having a given energy, having a given property. So for example, if it turns out that the first possibility is true, then this condition, new energy lower than the initial energy, entails that the multiplicity of the total system evaluated at the new energy, in other words, the number of states of the total system in which system A has the new energy, this multiplicity, this number of states, will be larger than the multiplicity evaluated at the initial energy. On the other hand, if it turns out that the second condition, the second possibility, is true, then this condition, new energy higher than the initial energy, entails that the multiplicity evaluated at the new energy will be larger than the multiplicity evaluated at the initial energy. Okay, so to sum up the story, suppose that we plot the multiplicity of the total system against the energy of system A, and we zoom in, we focus our attention on the behavior of the multiplicity around the initial energy. So when we say that there are two possibilities, we are stating that the multiplicity could be decreasing around this value or increasing. So for example, if possibility 1 is true, then we have more states when the new energy is lower than the initial energy. That's this condition. The multiplicity is larger when we are evaluating an energy which is lower than the initial energy, to the left of the initial energy. And of course, the multiplicity will be smaller if we are evaluating an energy which is higher than the initial energy. So at this point here. And if possibility 2 is correct, in other words, if a new energy higher than the initial energy entails a larger multiplicity, so that means that the multiplicity is increasing around the initial value. So a higher energy, so an energy to the right of the initial one, will have a larger multiplicity. So basically, what possibilities 1 and 2 amount to is that the multiplicity could be decreasing or increasing. So to find which condition is true, we need to identify the slope of the curve. And if the slope is negative, then we have more states having lower energy than states having higher energy. So it is more likely that system A will lose energy because it is more likely that the new property will be an energy which is lower than the initial energy just because we have more states having this property than states having the property higher energy. On the other hand, if possibility 2 is true, if the slope is positive, then we have more states with the property higher energy than states with the property lower energy. So it is more likely in this case that the energy of system A will increase. So it is more likely that system A will receive energy from system B. So to identify which possibility is the true one, we need to inspect the slope of the multiplicity. But instead of inspecting the slope of the multiplicity, we could inspect the slope of the entropy, because since the entropy is proportional to the log of the multiplicity, a negative slope of the multiplicity entails a negative slope of the entropy, and a positive slope of the multiplicity entails a positive slope of the entropy. So instead of inspecting the slope of the multiplicity, we're going to inspect the slope of the entropy. Okay, so we inspect the entropy instead of inspecting the multiplicity. And to do that, we define the variation of the entropy of the total system as being the entropy of the total system evaluated at the new energy minus the entropy of the total system evaluated at the initial energy. And we ask which sign of delta U results in a positive delta ST UA. In other words, which sign of delta U results in a positive variation of the entropy. So if it turns out that a positive delta U results in a positive variation of the entropy, so that would mean that this condition, positive delta U, resulted in this condition, a positive variation of the entropy. Recall that if this is positive, that means that this entropy is larger than this entropy, which means that this multiplicity is larger than this multiplicity. So positive delta U, UAN lower than UA naught, entailing positive delta ST, that can only be the case if possibility 1 is true. So if we identify that a positive delta U results in a positive variation of the entropy, we have identified that possibility 1 is the true one. In other words, we have identified that it is more likely that energy will flow from system A to system B than the other way around. On the other hand, if we find that delta U negative results in a positive variation of the entropy, then we have identified that this condition, in other words, negative delta U, resulted in this condition. And that is only the case if possibility 2 is true. In other words, we have identified that it is more likely that energy will flow from system B to system A than the other way around. Okay, so our job is to find the sign of delta U resulting in a positive variation of the entropy. If positive delta U results in a positive variation of the entropy, then it is more likely that energy flows from system A to system B than from system B to system A. If delta U negative results in a positive variation of the entropy, that means that it is more likely that energy flows from B to A than from A to B. And of course, we can also understand this by imagining a plot of the entropy against the energy. So if a positive delta U, recall that positive delta U means we are walking towards the left because of our definition. The new energy is equal to the initial energy minus delta U. So positive delta U, system A is losing energy, so we are walking towards the left. So if a positive delta U results in a positive increase of the entropy, then that means the slope is negative. We are walking to the left and the entropy is increasing. If a negative delta U, so recall that negative delta U, system A is winning energy. The energy of system A is increasing. So if a negative delta U, in other words, if we walk towards the right and then the entropy increases, that means the slope is positive. We have possibility 2. So now it's just a matter of a bit of mathematics. So the first thing we need to do is to express the total entropy in terms of the entropies of system A and B. So we begin by expressing the total multiplicity as the product of the multiplicities of A and B. We learned in the previous lectures why this equality is true. Now we take the natural log on both sides and we use the property of logs, that the log of the product is the sum of the logs. Now we multiply both sides by Boltzmann's constant, and it follows directly from the definition of entropy that the entropy of the total system is equal to the entropy of system A plus system B. And from this equality, it follows directly that a variation of the entropy of the total system is given by the sum of the variations of the entropy of system A and system B. Now we also know from calculus that if we have a function f of x, then a small variation of this function is given by the derivative of the function with respect to x times a small variation of x. So if we apply this identity to the particular case of the entropy, which is a function of the energy, then we get that delta S is given by the derivative of the entropy with respect to the energy times delta U times a small variation of the energy. And from the definition of temperature, we find that this term here is given by 1 over the temperature, so we get this expression for a small variation of the entropy. Using this expression here for the variations of the entropy of system A and system B, then we get this expression for a small variation of the entropy of the total system. Now recall from our convention that the new energy is given by the initial energy minus delta U when we are dealing with system A, and the new energy is given by the initial energy plus delta U when we are dealing with system B. So that means that delta UA, in other words, the new energy minus the initial energy, is equal to minus delta U. So we replace this term with minus delta U, the minus here, and this term, for the same reason, will be equal to plus delta U. So we replace this term with delta U. Now we just reorganize this expression a little bit to find an expression for the variation of the total entropy in terms of delta U and the temperatures of system B and system A. Now let's investigate what this equality entails. So for example, let's suppose that the temperature of system A is higher than the temperature of system B. So according to this expression, if TA is higher than TB, then a positive delta U results in positive variation of the entropy. Because if this term is higher than this term, that means that the term inside the brackets is positive, which means that we need a positive delta U to obtain a positive variation of the entropy. On the other hand, if the temperature of system A is lower than the temperature of system B, then the term inside the brackets is negative, which means that we need a negative delta U to obtain a positive variation of the entropy. Now recall that we had identified that if a positive delta U results in a positive variation of the entropy, that means that it is more likely that energy flows from A to B. And here we have found that a positive delta U results in a positive delta ST if the temperature of system A is higher than the temperature of system B. On the other hand, if delta U negative results in a positive variation of the entropy, then it is more likely that energy flows from B to A. And here we have found that a negative delta U results in a positive delta ST if the temperature of system A is lower than the temperature of system B. So joining everything together, we have concluded that if the temperature of system A is higher than the temperature of system B, that means that it is more likely that energy flows from A to B. On the other hand, if the temperature of system A is lower than the temperature of system B, then it is more likely that energy flows from B to A. So notice that in both cases, we've concluded that it is more likely that energy flows from the hotter to the colder system. So if we ask, why does energy flow from a hotter to a colder system? We could answer this question invoking the second law of thermodynamics. We can say that energy flows from a hotter to a colder system because this is the process that increases the entropy. As you have just seen, this is the process making delta ST positive. This answer is absolutely correct, but we should not forget the meaning of this answer. To state that a process increases the entropy is to state that the new property has more states to it than the initial property. In other words, that the new property is more probable than the initial property. So we can also answer the question of why energy flows from a hotter to a colder system by answering that this happens because this is what is more likely to happen. To state that the entropy increases is to state that the most probable event happened. Okay, so with that, we conclude this lecture, and in the next time, we're going to derive another very important result of statistical physics, the partition function. See you there.